Hi guys, so here's it number 3, the third video, and this is on covalent bonding. So we've treated ionic bonding already as well as the introduction, so you can check it out if you've not watched it yet. Now for covalent bonding, by the way, the full video is on YouTube at Copy Chemistry on YouTube, so you can check out the full video. Right, let's get into it. Covalent bonding. For ionic bonding, it involves complete transfer of electrons. And then for covalent bonding, it involves sharing of electrons. So we're sharing electrons here. And remember, this covalent bonding happens in molecules like this, H2N2O2. And also when you have the elements close together in the periodic table. For instance, you can have carbon, which is in group 4, and then oxygen, which is in group 6. So you could have a covalent bond formed here as well. So there are various examples of covalent compounds like H2O, NH3, and these other ones that I've given. So these are all covalent compounds. So we're going to see how they actually share these electrons. And let's start from the first one there, which is hydrogen, able to carry on with the other ones. Right, so we have hydrogen and another hydrogen molecule, because H2 is H and another H, right? So hydrogen has one electron like this. So what will happen here is that they would contribute equal amount and share equally as well. So this first one contributes his 1 here, and the other one contributes its 1 here. So now they both have 2 each, and they're both stable. You can also have oxygen and nitrogen doing the same thing. So let's try out nitrogen. So this is how nitrogen works. Nitrogen has 5 electrons in the outermost shell. So we have 1, 2, and then we have 1, 2, 3. And then another nitrogen also has 5, 1, 2, and then 1, 2, 3. So what happens here is that I could have these 3 combining with this 3 here. Imagine if they contribute 3, 3, and then they share it equally. It means that this one will have 6, and this one will also have 6. Okay, so if this one has 6, then plus this 2 here gives you 8. Same thing happens here. And that's why you can say that between nitrogen and nitrogen, you're going to have triple bonds. Between hydrogen and hydrogen, you have a single bond. Okay, so that's how it works. Now there's something about oxygen. When you want to draw this for oxygen, you'll find that oxygen is in group 6, right? So it has 6 outermost. 1, 2, 3, 4, 5, 6. And then your other oxygen molecule, 1, 2, 3, 4, 5, 6. So you might look at it this way, that if this should contribute 2 and this should contribute 2, then this one will have 4 and this one will have 4. So if I should add 4 from here with this 4 here, I'll get 8. And that would eventually look like I will have oxygen contributing 2 each, right? Meaning that I have a double bond. Here is contributing 3 each, meaning I have a triple bond. So this O to O double bond would then turn out to be like this. Okay. However, there are other indications of structures of oxygen molecule like this, O with a single bond. Okay, so oxygen will be a sort of an exception in this case. It's just that this structure here is preferred, okay? But according to what we're doing today, how to play with bonding, then you can go with this, okay? But note that this is the most preferred structure of oxygen when you get to the higher level. Now the bonding we're dealing in this case should cover for secondary school chemistry. It should also cover for GSC chemistry and also A-levels chemistry. you'll see it this way, okay? But generally, when you get to a higher level, you will learn that oxygen should be a single bond like this for some other reasons, which we're not going into right away, okay? But I just wanted you to know that so that you don't see it as contradictory. Okay, it's contradictory a word. Anyway, let's move on. So, yes, I really want to look at ammonia. So, do you know how ammonia would work? Ammonia is nitrogen with 3 hydrogens. So, let's check that out. NH3. It means that we need nitrogen, then we need hydrogen, hydrogen, hydrogen. Nitrogen has 5, right? 1, 2, and then 1, 2, 3. And our hydrogen, they all have 1. So what if this one and this one contribute and then they share it equally? This and this contribute 1 1 and share it. This and this contribute 1 1 and share it. It means that eventually I'll be having something like this. So this is what's going on now. This is my shell. Now this is the last hydrogen that is coming in. This other hydrogen here could come in like this, okay? And then this hydrogen here could also come in like this. So it's contributing and then it's sharing equally. So you can see now that your nitrogen is complete and also your hydrogen have successfully attained their duplet. So it is clear that nitrogen could combine with hydrogen this way to get your ammonia, and you have 2 lone pairs. These are lone pairs because they don't participate in bonding. Okay, so you can try out for H2O, okay, on your own, and I'd like to see if you got that. So your covalent compounds, generally these are things you need to note again. The covalent compounds are soluble if polar. Okay, if the structure is polar, then it could be soluble in polar solvent. However, most of them might be non-polar, like your nitrogen, hydrogen, they are non-polar. That's because you have the electronegativity close. You don't have like a large electronegativity difference like what you have in sodium chloride, okay? Because they are formed from elements that are close together in the periodic table. You would definitely have your electronegativity values close. Therefore, it may not be polar for some of them. However, for some of them, it is polar, okay? For instance, if you have SO2, that's going to be your SO3 could be polar, your BF3, you could have your NH3. What else? You could give more examples. Your CO2. These are examples. All these that I wrote here now are examples of covalent compounds. Now, some might be polar, some may not be polar. Okay, for instance, your CO2 is non-polar. Your BF3, the way the structure is, you could have the polarity that is distributed by this could be cancelled out by the polarity that is distributed by the other 2 fluorine. So eventually it could be non-polar as well. Okay, however, your SO3 could be polar based on the arrangement. Okay, so the summary here is that some might be soluble if polar, and some of these covalent compounds might not be soluble if they are not polar. Then your covalent compounds have a simple molecular structure. That is if you're dealing with simple molecules like this. And then you could also have your covalent compounds having a giant covalent structure. So for in terms of the structure now, it could be simple molecular and then it could also be giant. For simple molecules like these ones are written, these are examples of simple molecules. And then you can also have giant molecules like what you have in your carbon. That's your giant molecule. Your diamond, for instance. That's what I mean by the carbon there. Carbon in the diamond form. Okay. Now let's talk about the melting point. By the way, for ionic substances, they have high melting points and high boiling points. Yes. For covalent substances, they could have low melting point and boiling point, but at the same time, they could also have very high melting and boiling point. For instance, your diamond has a very high melting and boiling point. Okay, but for the small molecules, you could have low melting and boiling point. Right, so that is how that works. So please take note of all that. If you need to write them down and then go over them to study, please do that. So in the next video, we're going to be talking about a kind of covalent bonding which we call the dative covalent bonding. By the way, what we've treated today in this video is the ordinary covalent bonding. That is this one we just did. Yes, so we're going into the dative very soon.